Hello students, welcome back. Let's begin with the final segment of our topic of chemical equilibrium, the Le-Chatelier's principle. Let's start. So about Le-Chatelier's principle now. So what is Le-Chatelier's principle? The first thing which comes to mind. Okay. So Le-Chatelier's principle states that on application of an external stress to a system which is in equilibrium, the system will adjust itself in such a way that the stress is partially offset. Okay, so all which you are worried about the stress, it will be offset and an entirely new equilibrium will be reached. So the first thing which is, what is this stress? Okay, stress is nothing but factors that can affect as discussed earlier. All the factors that can affect the equilibrium are basically stress in Le-Chatelier's principle. Okay, now suppose the statement says if the concentration of reactants, okay, increases, where the equilibrium should shift. Fine. So what is the job of Le-Chatelier's principle? The job of Le-Chatelier's principle is that any equilibrium, say that if it is partial pressure of carbon dioxide by partial pressure of carbon monoxide and partial pressure of oxygen gas. Okay, so suppose that if this is the equilibrium and your equation for it will be CO plus O2 is reversing to CO2, 2 times CO2. So if this is the case, so increase in the concentration of reactant. So if I will increase the concentration of carbon monoxide and oxygen, where the equilibrium will shift to? Can I say I am applying a stress in this part? In order to liberate this stress, that means in order to consume the extra amount of reactant which I have added, I need to form some product. So can I say it will shift to right, because left to right obviously. Okay, or it will shift on the product side. Okay, increase in the concentration of product, can I say it will be just the opposite case, so it will be left, or can I say it will be reactant side? Okay, see, if you want to understand this concept very clearly, it is very simple. Otherwise at the same time it is really confusing. How? Once again, see, increase in the concentration of reactant. When you are increasing the reactant, obviously it will shift on the other side. The more pressure you applied on one side, it will try to move on to the other side. The more pressure you will apply in this side, as in the case 2, it will move to this side, that is the reactant side. Okay, fine. So here I have tabulated it. So can I say increase in the concentration of product, the reaction will shift to left side. Left side means on the reactant side. If you are increasing product, that is in the second statement, left side. Decrease in product, can I say it will now form the product, that is on the right side. Increase in reactant, it is basically the same thing. You increase the reactant or you decrease the product, the relative concentration of reactant is basically increasing, so it will move to right side again. And decrease in reactant, can I say it is virtually same thing as the first one, so the left side. Okay, self justified. Fine. Now see, what is this, what the image which I have taken is basically the image of a beaker which is undergoing this reaction. Okay, this reaction is going on. So solution at this color, this is the color, it means that the solution is at equilibrium. Okay, in B there is an increase in the concentration of SCN minus ions, okay, in this flask. In C you have increased Fe3 plus. In D there is an increase in the reactant, okay, which is FeSC. Now from the image can you can tell directly that B and C increase in the product, the reaction shifts in the left direction. Can you tell that they are basically the same pictures because they have the same color, same kind of orientation? So same kind of reaction is going both in B and C. So it is immaterial that whether you increase this reactant or both of this reactant together, the reaction is going to be formed in the reverse direction only. If you increase in the concentration of one or more reactants, will always favor the formation of the increase in the concentration of one or more products will always favor the formation of the product. So is the case when the increase in concentration of FeSCN minus. So can you see it is much lighter than this, so it represents a forward reaction, means now the reaction is moving in this direction because you have increased the reactant. Okay, so it is moving in the forward direction. Had it been in equilibrium, it would have been seen like a more of a orangish tint, but it is completely yellowish. Okay, completely giving that indicating that a forward reaction is going on. Okay, fine. So now we have an example here. Okay, so Kc is given, this value is for Kc, you have the temperature here, okay, and the concentrations are given, okay, of various species. And what are the initial concentration? No, they are equilibrium concentration. Okay, now the question says, suppose ammonia is added to the mixture such that its new concentration increases. So and the question is, use Le-Chatelier principle to predict the shift in the direction of the net reaction. Can I say, since ammonia is added, that means product, so the reaction will shift left. Why? Because ammonia is product, you add product, reaction will move here. Okay, according to Le-Chatelier's principle. Now they are saying that, can you confirm this based on your calculation of QC? I said yes, why not? Let us make it QC. QC will be NH3's concentrations whole square by nitrogen's concentration to the power 1 by hydrogen's concentrations to the power cube. No problem with that. So NH3 is how much? 3.65, because its increased concentration is now this much, correct? And then nitrogen concentration is how much? 0.683 to the power 1, and hydrogen concentration is 8.8 to the power cube. All you need to do is to calculate this. Okay, you have already given value of Kc, it will be nothing but 2.37 into 10 to the power of minus 3. Okay, so you have Kc, you have Qc. If you will calculate it, can I say by the application of Le-Chatelier principle that I don't need to even calculate it? What I will get is my Qc will be greater than Kc. I actually don't need to do that, I can see it. Why? Because I am increasing the concentration of the product, so the reaction has to go in the left direction. Therefore, it has to be the case of Qc greater than Kc, as we have already seen in our previous notes. Fine. Yeah. Changes in pressure. Okay, changes in pressure and volume. Okay, now we have seen that about the changes in concentration. Till now in the previous example also we changed the concentration of one of the product. Fine. Now we are going to see the change in the, what if I change the pressure of, I had, instead of changing the concentration of ammonia, I had changed the pressure of ammonia. Or what if I had changed the volume of the entire reaction mixture? How would that affect the equilibrium, and how would Le-Chatelier's principle be applied to that? That is, how would the reaction again attain equilibrium? Okay, so first statement is change will pressure will only concern gaseous reaction or gases. It is basically term for gaseous phase reaction, obviously. Okay, so now see, with the application of ideal gas law, how are we going to arrive at it? The pressure changes and volume changes. So both pressure and volume changes are going to affect the concentration of the gases. Okay, so this N by V is what? Moles per liter. Basically N is moles and V is in liter. Can I say it is concentration then? So changing in volume is going to affect concentration. A change in pressure at constant temperature, suppose that your temperature is constant, so a change in pressure is definitely going to affect a change in concentration. So can I say that changes in pressure and volume is going to affect the change in concentration, and we have already seen that change in concentration affects your QC and hence the equilibrium, and take decisions accordingly, that whether the QC was less than Kc, more than Kc, or remained equal to Kc even after changing the volume or the pressure. Okay, fine. So let us see. Okay, shift in equilibrium. Now increase in pressure. Suppose you have a reaction. Okay, let's take the same example, is reversing to 2 times ammonia. Okay, let's take this example also, and one more example, PCl5 is reversing to chlorine plus PCl3, and one more example, H2 plus I2 is reversing to 2 times Hi. Okay, now this is our reaction 1, 2 and 3. We will see the application of this on all the 3 reactions. So it is increase in pressure. So suppose I have increased the pressure, so the statement says that the effect will be in the fewest number of moles. That means when the moles decrease, can I say pressure decrease, because PV is equal to nRT. If N decreases and if the volume is constant and temperature is constant, then if N decreases, P has to decrease. So when you are increasing the pressure, the reaction will move in such a direction that the volume should decrease. So volume will decrease when number of moles will decrease. Okay, so what in case of reaction 1, where it should go? In case of when the pressure is increased. Okay, let us see where the volume are decreasing. Here 4 moles are there total, here only 2 moles are there. So on increasing the pressure, it will move here fewer number of moles, 2 moles and 2 moles. So on increasing the pressure, no change. Why? Because both of them are 2. So can I say that in this case Kc or Kp is independent of pressure? Okay, now let us see this. Okay, fewer number of moles, can I say it will move in the reverse direction, because assuming that PCl5, Cl2 and Cl3 all are in gaseous state, so it will move in the left direction. Okay, now decrease in pressure, can I say it will just be opposite to increase in pressure? So a decrease in pressure will be this, it will again be no change, and this will be in this direction with most moles. Okay, now increase in volume, when you increase the volume, the side with most moles. Okay, or can you say either when you increase the volume, the pressure decreases, because at constant temperature P is, so volume increases, pressure decreases. So what is decrease in pressure? Most moles, so most moles. So can I say it will be again in this direction, it will again be no change, and it will be in this direction. A decrease in volume, obviously opposite to that, and it will again be no change. Okay, understood? Fine. So this is about changes in volume and pressure. So what you are doing, how to do that change, it is basically the graphical representation, that how we are actually doing. In order to increase the pressure, what we will do, we will apply the force. Now the volume is constant, temperature is, because we are not heating it, and we have increased the pressure, okay, and obviously the volume reduced. Okay, why? Because when the temperature is constant, pressure is inversely proportional to volume. So when we increase the pressure, earlier it was nothing was there, only 8 atm atmosphere was there, so it was under atmospheric pressure, so it had a V1. Now it is having a small v. Why? Because I increased the pressure, so the volume had to decrease. Okay, fine. Now something like equilibrium position versus equilibrium constant, both of these are different thing, obviously. Let's see how. Now changes in temperature, first of all. Okay, it just depends that whether your reaction is endothermic reaction or your reaction is exothermic reaction. Okay, what is exothermic reaction? Exothermic reaction is basically that releases heat. Endothermic that absorbs heat. Okay, fine. So when you increase the temperature for an endothermic reaction, your K or the equilibrium constant value will reduce. Why? Because it is endothermic, it needs heat. Okay, you are giving heat, that means now the reaction will be favored in the forward direction, thus K will decrease. Opposite will happen when decrease in temperature, so the K will increase. In case of exothermic reaction, the same thing, but in the reverse case, I mean that now in this case the heat is released, so when you increase the temperature, the K will increase, when you decrease, it will decrease. Okay, fine. So let us see it by an example. Suppose this example of the molecular rearrangement again. Okay, it is a thermic reaction. Thermic reaction means that it is either gaining or losing heat. Now we will see that heat is released, or you can say that it is an endothermic reaction. The first way that it is written is an endothermic reaction. That means when N2O4 wants to go to NO2, it needs heat. See the equation which is written, heat plus. Whereas if NO2 wants to become N2O4, it will release heat. Okay, so what will happen to the change in temperature? So can I say it is an exothermic reaction, it is an endothermic reaction. So when you increase the temperature for an endothermic reaction, so where it will proceed? Can I say that if you are increasing the temperature, it will proceed in this direction, because here you are already having high temperature, you are giving high temperature, so it will obviously proceed to this direction. If you are decreasing the temperature, obviously the opposite. In this case, if you increase the temperature, here you are having high heat, you are increasing the temperature, can I say that you are adding something here, therefore it will move in this direction. If you decrease the temperature, obviously the opposite. That's it. Okay, now finally, effect of a catalyst. Catalyst is another substance which can affect your people say generally that chemical reaction, but catalyst does not affect equilibrium. Okay, but it affects the equilibrium position. Like I already said that I am going to say there is a slight difference between equilibrium position and equilibrium of a reaction. Catalyst can affect your equilibrium position but not the equilibrium. Why I say that? Equilibrium position is the amount of thermal energy at which the reaction is going to happen. Okay, it is basically the amount of the thermal energy at which the reaction is going to happen, or the amount of activation energy at which the reaction is going to happen. Now a catalyst will do nothing but change the path of the reaction or change the mechanism of reaction, such that now it takes low energy for completion. So now it changes such that it is now taking low energy for completion. Such kinds of elements are known as positive catalyst. Suppose it has changed the path such that it is taken more amount of energy for completion, it would be known as negative catalyst. Okay, fine. So since the catalyst does not alter the reaction but just changes the course of the reaction, it does not affect your equilibrium constant. That means Kc, Kp or Qc remain unaffected by catalyst. It just increases the rate of the reaction. So suppose if you have a gaseous mixture which attains equilibrium after 1 hour in the presence of catalyst, it will attain equilibrium at a time which is less than 1 hour. It will quickly attain the equilibrium, but the value of the equilibrium constant Kc will remain the same, will remain one and the same thing. So this was all about the effect of catalyst. Hope you enjoyed the session. If you have any doubt on the topic of chemical equilibrium, please browse to the site askIITians.com and click on discussion board. The next screen, select the right hand side, ask experts, choose your category from various drop down menu, post your questions here, and we experts at Ask IITian will answer all your queries within 24 to 48 hours. We have discussed in chemical equilibrium the basic principle of what is an equilibrium. Then we moved on to homogeneous and heterogeneous equilibrium, solved a few numericals, and also learned how to write down the various expressions of Kc and Kp under different circumstances. Hope you enjoyed that and your concepts are really clear. Now stay tuned for more videos on physics, chemistry, maths and biology on askIITians.com.